All right. At the end of the previous lecture, we talked about how we can build sequence-to-sequence models and improve their ability to handle long-range dependencies by using an attentional mechanism. And the attentional mechanism essentially shortcuts connections between every point in the input sequence and every step of the decoding process. In today's lecture, we're going to talk about another class of models for processing sequences that does not use recurrent connections, but instead relies entirely on attention. And we'll build up towards a class of models called transformers. So the question we can start with is, well, is attention actually all we need? Can we get away entirely with using attentional connections without any explicit recurrence? So just to briefly recap attention from last time, when you have a sequence-to-sequence model, as you're encoding the sequence for the parts shown in green, you also output a key at every step, represented with K1, K2, and K3. And when you're decoding for the parts shown in blue, at each step you take in your previous RNN hidden state, and you also output a query, for example Q2 or Q3, and then you compute dot products between your query at that step and all the keys in the encoding step, pass those dot products through a softmax to get essentially a probability on every step of the input, and then average together the hidden state activations for the encoder weighted by those probabilities. And this essentially indexes into the hidden state of the encoder for the time step that whose key most closely matches your current query. And in effect, this provides a kind of shortcut connection to carry information from an earlier step during encoding into the current step for decoding, which can improve your model in various ways. So let's start with this question. If you have attention, do you even need recurrent connections? Because in principle, attention can grab any information you want from the input string, so maybe instead of relying on recurrence to capture information about that input string, can you rely entirely on attention to capture this information? Or put another way, can you transform an RNN into a purely attention-based model? So here, you would have attention accessing every time step. So you need to be able to index into every step of the input, but you also need to index into every previous step of the output so that you can handle the structure prediction problem, so that you can actually see which words you predicted before. And in principle, if you do this, you can do everything that recurrence can and more, but with a few important caveats, and that's what we'll go through in today's lecture. So in order to get rid of recurrent connections like this, and rely entirely on attention, there are a few issues that we have to overcome. First, if we just do this naively using the same attentional mechanism shown on the slide, now at step L equals 2, we won't be able to access S1 or S0. So we can access H1, H2, and H3. We can access the hidden state of the encoder, but this attentional mechanism doesn't give us any way to access previous states of the decoder, which doesn't allow us to understand what the decoder was producing at previous steps. So the encoder now has no temporal dependencies at all, and each step of the encoder in this naive version is completely independent of every other step. And of course, we don't want that because words do have very strong dependencies between each other. So we have to fix this first, and then we'll see there are actually a few other problems that come up, but fortunately, all of them can actually be fixed. So first, let's describe a basic version of self-attention. So for this basic version, I'm not going to make a distinction between the input sequence and the output sequence. I just have one sequence, and I would like a purely attentional model that can basically process all of the steps of this one sequence jointly. And then we'll see towards the end of the lecture how we can return to sequence world later. So for now, we just have one sequence. Later on, we'll come back to sequence. For now, you can think of this as basically just kind of the language modeling part, so just the decoder without worrying about the encoder. Okay, so we're going to take all of the time steps of our sequence, and we'll encode each time step. So this is kind of some little feed-forward model. It's not a recurrent model, because there are no connections between the h's, but we still have weight sharing. So h1 is some function of x1, h2 is some function of x2 and h3 is some function of x3, and it's the same function in each case. So for example, if it's some nonlinearity applied to a linear layer, then we might have the same weights in the linear layer for every time step, but the time steps are not actually communicating between one another. Okay? And in general, we could use any nonlinear function. And it's typically a learned function. And then we're going to produce a value for each time step. So this is just like that advanced version of attention that we saw at the end of the previous lecture, where vt is some function v of ht. Before we just had usually vt of ht is just equal to ht in the basic version of attention. Now we're going to use linear transformation. So we're going to say that v of ht is some matrix wv applied to ht, and it's the same matrix wv at every step. So the value is a linear transformation of the hidden state. For example, it could be a function that maybe masks out certain values of ht. Maybe it takes those parts of ht that are relevant for values and discards the rest. Or maybe it transforms them in some more complex way. wv is going to be learned. And we'll see soon why it's important to have a learned value. We're also going to output a key at every time step. So far this looks just like the encoder part of the classic attention. So the key is also going to be some function of ht, and just for simplicity we'll say that it's also a linear function. So kt is equal to wk times ht. And this is the part that's different, every time step is also going to output a query. So it's like the encoder and the decoder together. So every step outputs a value, a key, and a query. And the query, of course, is also a function of ht. And for now, we'll say it's also a linear function. So qt is just wq times ht. Okay, so far so good. We've got a key, a value, and a query, and all of them are linear functions of ht. Okay, and then we'll do exactly what we did with attention before, except that now there's no distinction between an encoder and a decoder. So essentially, every step can index into every other step, including itself. So we'll compute dot products between every qt and every kt. And those will give us our attention scores, E11, E12, E13, E21, E22, E23, and E31, E32, and E33. So if we have 3 time steps, we have 9 attention scores. And then we'll do exactly the same thing as before. We'll pass each of them through a softmax. So we'll get these alpha values, and we normalize over the keys, right? So for every time step L, we normalize over the T's, right? So we want to get a separate softmax vector for every time step. So corresponding to every query, we get, for every query QL, we get an alpha L1, an alpha L2, and alpha L3, okay? So these sum to 1 over the T's. They do not sum to 1 over the L's, of course. And then we do exactly the same thing that we did before. We take the values at every step, we weight them by the alphas, and that gives us the attention at time step 1. So if you have alpha 1, 1, alpha 1, 2, and alpha 1, 3, you compute your attention as alpha 1, 1 times V1, alpha 1, 2 times V2, alpha 1, 3 times V3, sum them all up, and that gives you A1. That gives you the attention output at time step 1. And in the same way, you compute the attention output at time step 2 as alpha 2, 1 times V1 plus alpha 2, 2 times V2 plus alpha 2, 3 times V3, sum them all up, and that gives you A2, the attention at the second time step. So now this self-attention mechanism has produced an attention vector at every time step. So we start off with an input at every time step, we get an H at every time step, then we have this self-attention process which combines information from different time steps and produces a different output, A1, A2, and A3 at every time step. So you can think of this as a kind of layer. It's basically a layer that integrates information across the time steps. Okay. So we could build an entire network out of such self-attention layers. So in this network, we would take our input at every time step, get the corresponding H's with some transformation. For each one, we have a key, a query, and a value. We pass those into this self-attention layer. It's a kind of layer, and that produces an activation at every time step. And then we can repeat the process. We can have a key, a query, and a value computed using a different set of WK, WQ, and WV matrices passed into another self-attention layer, and so on and so on. And we can repeat this process, and each step of this self-attention processes the sequence more and more. And in this way, we can transform an input sequence of one sort, maybe a sentence in French, into a different type of sequence like a sentence in English. Okay, so we keep processing until we've processed this enough, and then at the end you have to somehow decode it into an answer, and we'll talk more about that later. Okay, so that's the basic idea for self-attention. And this basic idea, we're going to use it to build a new class of sequence-to-sequence models. Now, the actual process of turning this into a viable model requires a number of additional steps. So, the basic concept of self-attention can be used to develop a very powerful type of sequence model called a transformer. But to make this actually work, we need to develop a few additional components and address some fundamental limitations of self-attention. And this will actually take us most of today's lecture. So here are the things we need to take care of. The first one is something called positional encoding. And positional encoding addresses an issue with self-attention, which is that self-attention, unlike recurrence, does not have any notion of proximity in time. So all those x's, x1, x2, and x3, were processed entirely in parallel without any regard for their order. If we had switched their order, the self-attention layer would produce exactly the same answer. So it's completely order invariant, and that can be a big problem when dealing with data like natural language, where the order of the words actually matters. So we'll need to address this somehow. Second, we'll develop something called multi-headed attention, where at each layer we don't just have one value in query and key, but we can actually have multiple so that we can do more complex operations. You can almost crudely think of key value query tuples as kind of filters like in a convnet. And in practice, you would never build a convnet with just one filter per layer, in the same way you don't want to build a pure self-attention model with just one attention head per layer. So we'll talk about how we can build multi-headed attention to allow querying multiple positions at each layer. Then we'll talk about how we can add appropriate nonlinearities into self-attention models. And this is actually very important because so far, the self-attention mechanism that we've discussed is actually entirely linear, meaning that the activations at the next self-attention layer are entirely linear in the activations in the previous one, with the exception of those weights. So remember that AL is a sum over all the positions of alpha LT comma VT. So it's actually linear in the VTs, it's linear in the values, and the values are linear functions of the H's. The alphas are nonlinear, but the values are linear. And that can actually be pretty limiting when it comes to the expressive power of self-attention layers. And then lastly, we'll talk about a very important detail called masked decoding, or masked attention. The problem that this is addressing is that the attention mechanism doesn't distinguish between past and future. So an RNN, when it progresses one step at a time, it looks at the past, but it doesn't look at the future, which makes it possible to use an RNN to decode, meaning that you generate a word, then condition on that word and generate the next word, then condition on that word and generate the next word. It's not clear how to do that with self-attention, because self-attention looks at all the time steps, both past time steps and future time steps, to compute the attention at the current time. And that is sometimes a good thing, but it can be a very bad thing when you're trying to use self-attention for a language model to decode. And we'll talk about how to address that issue. So we'll go through each of these 4 points in the next part of the lecture.